Last time in separations, we started to solve a countercurrent liquid-liquid extraction design problem by first drawing a big box around all the stages and doing a material balance to find the outlet product streams. So this is what we were given last time. We started with 100 kilogram per hour feed that was 30% solute, so acetic acid, and 70% diluent, which is water. And to the other side, we fed 200 kilograms per hour of solvent, so 100% vinyl acetate. And we were also given the design specification that the outlet water stream, or the outlet raffinate, had to be 5% acetic acid. And last time I talked about how if we know that one of the outlet streams, which is coming from a stage, so if I just sketch in stage N here inside the overall process, because it comes off of a stage, it has to be in equilibrium with something. Therefore, the composition must be on the equilibrium diagram. The feed point is there, the solvent point is there, the feed point is over here. And last time we talked about how to find the overall mixing point. We found that the overall mixing point was 67% vinyl acetate. So this is M overall. And we set about first finding what our unknowns are. So I have an unknown E1 flow rate, an unknown RN flow rate. And I had stopped short last time of solving for what the flow rates were. So just to remind you, this point, which is RN, has 5% acetic acid, but it also has 92% water and 3% vinyl acetate. And before I go through like recapping how you find it graphically, I want to make a quick point in that you could have solved this problem as a material and energy balances student. So I have to fill in the compositions here. So I have a composition of acetic acid in the E1 stream, and I also have a composition of vinyl acetate in the E1 stream. You also have a composition of water, but I can write the physical constraint that 1 minus XAA E1 minus X VA E1 is equal to X water E1. So I'm going to omit that for the purposes of doing a degree of freedom analysis. So my degree of freedom analysis just on this system as it stands right now, I've got E1 as an unknown, composition of acetic acid, composition of vinyl acetate, and RN as unknowns. So I have 4 unknowns in this process. I have 3 material balances. I can write 1 material balance for each component of my system. 3 material balances. And then finally, I have 1 relationship between the acetic acid composition and the vinyl acetate composition. So I'm going to write this as -1 for a relation between X AAE1 and XVAE1. I'll call this a phase equilibrium relationship. In other words, it's not necessarily a physical constraint like the equation that I drew up here is. The fact is that the composition of acetic acid and vinyl acetate are tied together because they must lie on the phase envelope. Therefore, if I knew, which I don't know, but if I knew what the coordinate for acetic acid was, I would be constrained to be somewhere on this line. So it takes away one of these degrees of freedom. So back to the overall DOF analysis, I've got 4 minus 3 minus 1. That is, of course, equal to 0, which means that I can theoretically solve this problem. And I could do it with the following equations. I'd have to write out all 3 material balances. So I'd start by saying that F plus S is equal to E1 plus RN. And in order to solve this problem graphically, what I do is I make it equal to the overall mixing point, M. So it's M0 for overall mixing point. I can also do 2 other material balances, and I'm going to write them in the general form here to save a little bit of time. So the composition of component I in the feed times the feed flow rate plus the composition of I in the solvent stream times the solvent flow rate must equal the composition of component I in the extract coming off of stage 1 times that flow rate plus xi Rn times Rn. And that is all equal to, I can do a mixing point evaluation here, xi of the mixing point times the mixing point. So these are the three equations. And then my last equation is that this relationship in the phase equilibrium. And recall that this comes from the NRTL model, which we're not going to get into in this class. I'm just going to use the graphical method. So the fact that I can say that F plus S is equal to M, and similarly E1 plus Rn is also equal to M, means that they both must lie on lines with each other. So F, S, and M are on the same line. E1, Rn, and M are on the same line. So I already have a mixing line that connects F to S, and I know where Rn is. So if I know where M is, I can draw a line, make these collinear. And if I'm constrained that it must be on the phase equilibrium envelope on the other side, I now know the location of E1. All right, so this allows me to solve for my E1 and Rn flow rates. I didn't actually solve for these last time. So if you want to try and do that now, I encourage you to do so. The answers that I got were that E1 is 236 kilograms per hour. And the composition of E1 is, the acetic acid composition is 12%. The vinyl acetate composition is 84%. And that makes the outlet raffinate stream is 64 kilograms per hour. So that's how we left off last time. We've gone from having a problem where very little things were specified, or I had more than 1 degree of freedom in every single stage, to now I should have 0 degrees of freedom on the first and last stages. So let's go ahead and start with just doing a balance on stage 1, or analyzing stage 1. And I want to make the point that I could have just as easily have chosen to analyze stage N. I know the exact same amount of information about stage N. I think it just makes a little bit more sense to work left to right, or starting with stage 1 instead of stage number to be determined. And if I sketch in what I know now what my composition is of E1, so 236 at 12% acetic acid and 84% vinyl acetate. My feed is still 100 kilograms per hour, and the composition is still the same. I'm going to keep the notation the same, 30% acetic acid, 70% water. Okay, now I'm going to run into a bit of a problem, all right, because I don't know what E2 is. I don't know what any of the compositions of E2 are. So I'm going to call it XI-E2. Remember, there's 3 variables there. 2 degrees of freedom because the 3 composition variables are not independent. And I have R1, and I also don't know any of the compositions of R1. Well, I suppose I do know what the compositions of R1 are if I say that I have phase equilibrium between them, but I'm still missing a crucial point of this analysis. I can't get anywhere closer after I know what these compositions are. And that's because typically in cross current, we found where the mixing point was. So I would say that F plus E2 is equal to M, and this must also be equal to E1 plus R1. Except the only variables that I know in this equation that I've drawn is F and E1. So therefore, I can't calculate what the mixing point is because I don't know E2 and I don't know R1. So I'm a bit stuck here. I can't do the mixing point, so I have to figure out something else. And then in the interest to keep the video short and digestible, I appreciate the feedback that a lot of you have given me on the essays, that you all like the short segmented videos. So I'm going to try and follow that advice, or keep that advice. And I'm going to stop this video here on the note that we cannot solve for the mixing point anymore. We need an analogous point.